In the previous class, we realized how different can be executed an application on a processor with respect to an FPGA. We saw that with respect to computational throughput and memory bandwidth, the HLS compiler achieved the best out of the capabilities of the FPGA resources through the processes of scheduling, pipelining, and Dataflow. But we did not provide any better explanation on what these three processes are doing. Therefore, it's now time to get closer to them and see what are they doing. Generally speaking, as we can also read from Wikipedia, scheduling is the method by which work specified by some means is assigned to resources that complete the work. In our context, scheduling means the ability of identifying the data and control dependencies between different instructions to determine the order in which each one will be executed. In the FPGA scenario, we are not working with a known and fixed set of computational units, and resources can be adapted and configured according to the needs to implement the desired set. Here, the scheduling process refers to the possibility of parallelizing the software algorithm for an hardware implementation. Within this context, we can focus on dependencies between adjacent operations as well as across time, guaranteeing that the desired computational units will have enough available resources to be implemented on the FPGA at a specific time. This allows the compiler to group operation in function, to execute in the same clock cycle, and to set up the hardware to permit the overlap of their executions. Being able to overlap the execution of a set of operations removes the processor restriction that requires the current function call to fully complete before the next function call to the same set of operations can begin. This overlap is exactly the main idea behind the pipeline process. Pipelining is a performance optimization technique based on the overlap of the execution of multiple instructions deriving from a sequential execution flow. Pipelining exploits the parallelism among instructions in a sequential instruction stream. The idea is to avoid data dependencies and increase the level of parallelism in an hardware implementation of a given function. The data dependency in the original software implementation is preserved for functional equivalence, but the required circuit is divided into a chain of independent stages. It's important to notice that all these stages, considering that they are supposed to run in parallel, has to share the same clock cycle. As an example, we can consider the following function: epsilon equal a plus b plus x all times d. One possible implementation can be obtained by using two adder blocks and one multiplier to implement this function. This implementation is purely combinational, and it's behaving as the corresponding software function, since all the input values must be known at the start of the computation, and only one result epsilon can be computed at a time. The overall execution can be computed without taking into consideration the delay in propagating the signals, as the execution time of the first adder plus the execution time of the second adder plus the execution time of the multiplier. Just to provide a better understanding, let us assume 10 nanoseconds to complete the execution of the multiplier and 5 nanoseconds for the others, which means that the time needed to compute the epsilon values is 20 nanoseconds. Now, within this context, the time needed to compute two subsequent values of epsilon is 40 nanoseconds, which is 20 nanoseconds times 2. The time needed to compute three subsequent values of epsilon is 60 nanoseconds, and so on and so forth. Now, what we are looking for is a way to overlap the execution of multiple instructions, and the way in which we are going to do this is by moving from a pure combinational logic to a sequential one. In this figure, we can appreciate a pipeline version of the previous circuit. The squares that we introduced in this circuit represent registers that are implemented by flip-flop blocks in the FPGA. Within this context, we are creating the chain of independent stages that we were previously describing, where each box can be counted as a single clock cycle. Therefore, in the pipeline version, the computation of each result epsilon takes 3 clock cycles instead of 1, as it was in the previous example. This doesn't seem to be an optimization, but we do have to remind that it is not important only the number of clock cycles per se, but clock frequency and the throughput. By adding the register, each block is now an isolated unit of computation. This means that the section with the multiplier and the section with the two others can run in parallel and reduce the overall computational latency of the function. Now, the time needed to complete the computation of the two others is 10 nanoseconds, which is also the same time needed to complete the multiplication. Within this context, we can reduce the overall clock cycle from 20 to 10 nanoseconds. Let us now consider the case, as we did with the circuit without pipelining, of the presence of multiple inputs. In the previous example, to obtain two values of independent epsilon, we had to wait for 40 nanoseconds. While now, by running both these stages in parallel, the circuit is essentially computing the two values of epsilon in parallel. The initial computation of epsilon, which is also referred to as the pipeline fill time, takes 3 clock cycles. However, after this initial computation, a new value of epsilon is available at the output on every clock cycle, because the computation pipeline contains overlapped datasets for the current and subsequent epsilon computation, which means that two independent values of epsilon can be computed in 40 nanoseconds. Wait, 40 nanoseconds? What? Where is the improvement? Well, wait a second. Consider the case with the computation of 3 independent values of epsilon. In the previous case, we had to wait for 60 nanoseconds, 20 nanoseconds times 3. Now, we are going to wait 50 nanoseconds, 30 nanoseconds for the computation of the first epsilon. But after the first 10 nanoseconds, we can start the computation of a second set of inputs, which is the same things with the following 10 nanoseconds. Finally, let us briefly introduce the Dataflow optimization process. When we are writing an algorithm that has to be executed in software, usually this will be executed sequentially. There is nothing wrong in doing this, but this is exactly the idea also behind parallel computation and parallel architectures. What if we are going to have a series of independent functions that have to wait to be executed? Not because they need the data to start their execution, but because they are waiting for computational resources to be available. Well, this is obviously something that we want to avoid, and that is why we are now working with multi-core processors. But what if our underlying hardware can be adapted to meet, by nature, such a condition? Well, this is exactly the case of an FPGA. Even when working with multi-cores, we cannot guarantee that we are going always to have all the cores used to execute our application, which is leading us in wasting resources. With an FPGA, this is not going to happen. We can adapt it to implement the necessary computation units according with the application needs. Within this context, the goal of the Dataflow process is to express parallelism at a coarse grain level. The SDXL compiler extracts this level of parallelism by evaluating the interaction between different functions and the loops of a program based on their inputs and outputs. The SDXL compiler can also extract this level of parallelism for functions and loops within a loop. I'm not going here to provide a better example on how to use the Dataflow idea to optimize our application, but we are going to hear more about this process in the near future. Don't worry.